Today, we'll explore nearest neighbor classifiers. Let's dive into how this algorithm works and its applications. Building on the basics of nearest neighbor classifiers, let's start with how they operate. This involves understanding the core terminology and mechanics. We'll explore issues around measuring similarity, particularly the challenges of using distance metrics. Next, we'll discuss the expressiveness of the nearest neighbor approach, which refers to its ability to capture complex data patterns. We'll also look at practical implementations in Python, providing hands-on insights. Finally, we'll consider the characteristics of this method, examining its strengths and limitations. This comprehensive overview will help you understand where and how to effectively apply nearest neighbor classifiers. The basic idea of nearest neighbor classifiers can be summed up with the phrase, "If it walks like a duck, quacks like a duck, then it's probably a duck." This highlights the principle of similarity-based classification. In the illustration, we see a test record being compared to multiple training records. The process involves computing the distance between the test record and each training example. After calculating these distances, we select the k nearest records. This selection helps in making predictions based on the majority class among these closest neighbors. This method leverages the concept that similar instances exist in close proximity within the feature space, allowing for effective classification based on known examples. This approach is intuitive and straightforward, making it widely applicable in various domains. Continuing with nearest neighbor classifiers, let's look at the broader category of instance-based classifiers. A rote learner is one type, which memorizes training data and assigns classification only if the attributes exactly match a training example. This approach lacks generalization, meaning it can't predict for unseen data unless there's an exact match. In contrast, the nearest neighbor method, like k-nearest neighbors KNN, selects the k closest points for classification. This method generalizes by considering proximity in the feature space, allowing for more flexible predictions based on similarity. Often, nearest neighbor methods are used interchangeably with instance-based classifiers because they rely on specific instances for decision-making, rather than constructing an explicit model. This makes them versatile tools in various applications. Here, we have another example of the nearest neighbor approach. The graph plots abdomen length against antenna length to classify an unseen instance. In this scenario, if the nearest instance to the unknown data point is a katydid, the class is determined to be katydid. Otherwise, it is classified as a grasshopper. The red symbols represent katydids, and the blue symbols represent grasshoppers. This visual illustrates how the nearest neighbor method uses proximity to known data points to make classification decisions, highlighting its effectiveness in distinguishing between similar yet distinct classes based on feature space. This approach is powerful for its simplicity and intuitiveness in handling classification tasks. For the nearest neighbor method, three key components are essential: a set of stored training records, a distance metric to measure similarity, and the number of nearest neighbors, denoted as k. To classify an unknown record, you begin by computing the distance to every training record. This involves using your chosen distance metric, such as Euclidean distance, to quantify similarity. Once distances are calculated, you identify the k nearest neighbors. The classification is then determined based on these nearest neighbors, typically using a majority vote or weighted vote approach. This ensures that the classification reflects the characteristics of the closest data points. This process highlights the practical steps and considerations in implementing nearest neighbor classifiers effectively. Nearest neighbor is an example of a lazy learner. Unlike eager learners, which perform work up front to build an explicit model from the training data, lazy learners defer this work. A lazy learner stores the training data during the learning phase without building a model. Instead, the computational effort is postponed until the testing phase, where classification occurs. At this point, the algorithm uses the stored data and metrics to make decisions without having an explicit model. This approach contrasts with eager learning, where a model is generated to describe the target function early on. Lazy learning can be advantageous in situations where model building is complex or unnecessary for the task at hand. When measuring similarity in nearest neighbor classifiers, several issues can arise. Irrelevant and redundant features can skew the similarity metric. It's often beneficial to perform feature selection to remove these features and enhance accuracy. Different scales and ranges across features can also pose problems, making normalization essential to ensure fair comparisons between features. Additionally, the default assumption that all features are equally important can be misleading. Differing feature importance needs to be considered to ensure the similarity metric accurately reflects the data's true characteristics. Addressing these issues is crucial for effective nearest neighbor classification. Assessing similarity isn't straightforward. For instance, a computer might determine that two images of a cartoon character are extremely similar, yet humans can notice subtle flaws or differences, such as in the finer details of one character. Conversely, images that appear superficially different to a computer, like an X-ray and a real-life depiction, can be perceived as similar by humans because of contextual understanding. This highlights the challenge in designing algorithms that accurately mirror human perception of similarity, emphasizing the complexity in capturing nuances that humans effortlessly recognize. When dealing with different scales in data, it can skew the perception of closeness. Here, we have two examples, John and Rachel, described by age, income, and number of credit cards. Closeness is measured using Euclidean distance, which calculates the square root of the sum of squared differences across features. However, because income has a much larger scale, it can dominate this calculation, overshadowing the impact of other features like age. To address this, it's important to rescale features to a uniform range, ensuring that no single feature disproportionately influences the distance metric. This adjustment helps create a balanced assessment of similarity across all features. Here, we see the impact of different scales on nearest neighbor classification. In the left plot, the x-axis is measured in centimeters, while the y-axis is in dollars. The nearest neighbor to the pink instance appears to be a specific class. In the right plot, changing the x-axis to millimeters affects the nearest neighbor, which is now blue. This demonstrates how scale differences can alter proximity calculations. To address this, z-normalization is recommended. This technique adjusts feature values to have a mean of 0 and a standard deviation of 1, using the formula x frac x minus text mean text stead x. This ensures consistent scaling across features, improving the accuracy of similarity assessments. When dealing with irrelevant features, consider a scenario where each example has 20 attributes, but only 2 are relevant. Even if examples have identical values for these 2 attributes, they may still appear distant in a 20-dimensional space. To mitigate the impact of irrelevant features, you can increase the number of training instances, making it harder for noise to obscure patterns. Consulting experts to identify and remove irrelevant features is also effective. Statistical tests can help prune these features, ensuring only the most relevant ones are retained. Additionally, searching feature subsets, as discussed in the data module, can further refine the feature set, enhancing the accuracy and efficiency of your model. Here, we're reviewing the expressiveness of 2 models, a decision tree DT with 2 splits, resulting in 3 leaves, and a linear model. The decision tree makes only 1 error, while the linear model makes 3 errors. This highlights the decision tree's ability to capture complex patterns with nonlinear boundaries, whereas the linear model is constrained by its straight line. The comparison underscores how different models handle data variability and complexity, illustrating the importance of choosing the right model based on the data's characteristics. The expressiveness of the one nearest neighbor, 1NN model, is illustrated here. This model achieves 0 errors by using a decision boundary that only appears where classes differ on each side. The boundary line indicates points equidistant between the nearest circle, one class, and plus sign, another class. This ability to create flexible, nonlinear boundaries allows 1NN to adapt closely to the data, capturing intricate patterns without error in this example. This demonstrates the model's strength in accurately classifying data based on proximity in the feature space, leveraging its detailed spatial awareness. The expressiveness of the one nearest neighbor, 1NN model, is further illustrated with boundaries around each example. The orange line represents these boundaries, showing different class labels on each side. These boundaries are implicit, naturally occurring as part of the Voronoi diagram, which partitions the space based on proximity to the nearest data point. While you can pre-compute these boundaries with effort, it becomes complex if k is greater than 1. This diagram visually demonstrates how the 1NN model classifies data by defining regions where each class dominates, highlighting the model's adaptability in capturing intricate data patterns. Using more than one nearest neighbor, as shown here, can create a more robust classifier. With k equals 1, the model becomes less sensitive to noise, meaning a single outlier point won't determine the class. Voting is a common method for combining the decisions of multiple neighbors, but you can enhance this by weighting votes by the inverse square of distance, giving closer neighbors more influence. In the diagrams, k equals 1 uses only the nearest point, while k equals 3 considers multiple neighbors, providing a more balanced classification. This approach improves reliability and accuracy, especially in noisy datasets. In this scenario, we're estimating class probabilities for a new point represented by the blue square. The classes are government, science, and arts, shown in green, red, and white respectively. To determine the probability of the new point belonging to the science class, we consider its neighbors within the defined boundary. The probability is calculated as the ratio of science instances to the total instances within this boundary. Here, the probability of science is 1/6, indicating one science neighbor out of 6 total neighbors. This approach helps quantify uncertainty and make informed predictions based on the distribution of nearby classes. Nearest neighbor can be effectively used for regression tasks, where the goal is to predict numerical values. To do this, you can take the average or median value of the k nearest neighbors. This approach helps smooth out noise and provides a robust prediction based on local data points. Additionally, you can weight these values by the inverse square of their distance from the test instance. This gives more influence to closer neighbors, improving the accuracy of the prediction by emphasizing the most relevant data points. This method leverages proximity to make precise numerical predictions. Here's a practical application of the nearest neighbor algorithm using Python. This script explores varying values of k. First, the necessary libraries are imported: kneighbors classifier from sklern.neighbors and matplotlib.pyplot for plotting. The training data xtrain and labels ytrain are prepared beforehand. The script iterates over different values of k stored in numNeighbors. For each k, a neighbor's classifier is initialized with the Minkowski metric, which is equivalent to Euclidean distance when p equals 2. The classifier is trained using clf.fit xtrain ytrain. Predictions are made for both the training and test sets using clf.predict. The accuracy for each k is calculated and stored in train.ac and test.ac. Finally, a plot is generated to compare training and test accuracy across different k values, helping visualize how k impacts performance. This approach guides the selection of an optimal k for the model. In this practical evaluation of the nearest neighbor algorithm, we see that test set performance peaks with 20 nearest neighbors. This suggests that a higher k value helps generalize the model better, reducing overfitting. Conversely, training set performance is highest with k equals 1. This is because each point is classified based on the nearest data point, resulting in perfect training accuracy. However, this can lead to overfitting, as the model captures noise rather than general patterns. Balancing k is crucial. A low k can cause overfitting, while a moderate k can improve test accuracy by smoothing decision boundaries, as observed here. This emphasizes the importance of selecting an optimal k for robust model performance. To conclude our exploration of k nearest neighbors, KNN, let's summarize its pros and cons. Pros: quick training due to its nature as a lazy learner. Easy to explain and justify decisions. Robust to noise when k1. Highly expressive, allowing complex decision boundaries. Versatile, applicable to regression tasks as well. Cons: relatively long evaluation time. Requires saving all training examples. Lacks a model for high-level insights. Sensitive to irrelevant and redundant features. Necessitates careful engineering of the distance metric. Overall, KNN is a powerful tool for classification and regression, but it requires thoughtful consideration of data preparation and parameter tuning to maximize its effectiveness. To conclude our exploration of K-nearest neighbors, KNN, let's summarize its pros and cons. Pros: quick training due to its nature as a lazy learner, easy to explain and justify decisions, robust to noise when K1, highly expressive, allowing complex decision boundaries, versatile, applicable to regression tasks as well. Cons: relatively long evaluation time, requires saving all training examples, lacks a model for high-level insights. Sensitive to irrelevant and redundant features, necessitates careful engineering of the distance metric. Overall, KNN is a powerful tool for classification and regression, but it requires thoughtful consideration of data preparation and parameter tuning to maximize its effectiveness.